Seagrass meadows are not the most conspicuous of ecosystems. Yet the green fields that once covered Europe's intertidal flats are an important habitat for many species. They provide shelter and resources for birds and fish. In addition, they accrete sediment and provide coastal protection. In the past decades, however, seagrass meadows have become a rarity. Extensive efforts have been made into restoring the seagrass meadows, with little success, unfortunately, as restored seagrasses would typically disappear within a few years. If there was one thing clear from failed restoration experiments, is that we understand little of the dynamics of seagrass establishment. What does it take for seagrass plants to survive? How can we identify and monitor successful seagrass establishment? Dr. Koen Siteur from the Royal Netherlands Institute for Sea Research has developed a generic mathematical model for the dynamics of seagrass vegetation.
I have a background in modeling desert ecosystems where plant growth and competition for water results in large-scale spatial patterns. And these spatial patterns you can use to determine the resilience of these ecosystems and to guide and monitor restoration efforts.
It turned out that the principles of pattern formation from arid systems do not apply one-to-one to seagrass meadows. Plant growth in arid system is driven by the availability of rainwater. Seagrass growth, on the other hand, is determined by the presence of nutrients, light and fine sediment. Would this make a big difference?
When we analyzed the model, we found that the patterns were actually very different from those found in desert ecosystems. The patterns look much more like patterns found in physical systems.
The patterns in the model form through a mechanism known in physics as phase separation. Phase separation occurs when we mix two liquids, such as water and oil, that slowly separate over time. Physical theory on phase separation provides crucial insights in how to monitor and understand restoration success.
There's a couple of important lessons we can learn from physics theory. First, small patches may not do very well, while at the same time large patches may expand and attract more resources. The dynamics of patches may be very useful, for instance to study from drone images. Second, we can use the statistics obtained from these drone images to help understand the fate of these seagrass beds, and thereby we can aid in the monitoring of the restoration of seagrasses.
It turns out that the new theory not only applies to seagrass meadows, but to many other patchy ecosystems, for instance to natural grasslands. Grasslands are often a mosaic of patches with short grazed or tall grasses, strikingly similar to what is found in seagrass beds. The theoretical indicator framework derived from physical theory may therefore one day be used to restore and monitor ecosystems worldwide, and help managers and policymakers in protecting valuable patterned ecosystems.